In this lecture, I'm going to focus on class-based object-oriented languages, and we're going to look at how they define methods and invoke those methods. Let's start just by looking at the following example and thinking about what gets invoked in this case. I've got three classes, animal, and two specific kinds of animal, bird and cat. Each of these just has a toString method that tells you what kind of thing it is. I can create an array of animals that includes a bird and a cat, then iterate through those animals and ask them to print themselves. The question is, what do I get? In Java, the answer is going to be bird and cat. What's happening here is that we are using the dynamic type of the object, not the static type of the variable x. So note that x here has type animal, but it's bound to an object, first of type bird, then of type cat. Since Java uses the dynamic type, or the actual object type, to look up the methods, we actually get the methods for birds and cats getting invoked here when we call toString. This is different from what happens in C++ by default. Here's the same code written down. This is an array in C++ of a bird pointer and a cat pointer. Note in Java, we always have objects by pointer or by reference. So this is the corresponding code in C++. And I'm going through the array of references here and just outputting each one of them. What I get in C++ is not bird cat, but animal animal. What's happening here is static dispatch. That means that the method that's being invoked here is being chosen based on the type of the variable x. So since x is a pointer to an animal, C++ invokes the toString method of the animal class. You can get dynamic dispatch in C++, of course, but it's not the default. In order to get this in C++, you need to add the keyword virtual to this method. And when you access a virtual method through a pointer or reference, you'll get dynamic dispatch in C++. When people talk about C++, they often leave out this second requirement. If we access an unboxed object in C++, we always access it at the type of the variable that's being assigned. Here I have an array of birds and cats, not references, but an array of actual birds and cats. And what happens here is because the variable is declared at type animal, C++ doesn't allocate enough space to store all of the data that I could potentially have for a bird and a cat. We only have space for an animal. What happens here is a coercion or a truncation. The object bird is truncated to an animal. So what's stored here in this array is actually animal objects, not bird and cat objects. These two choices in C++, to have methods virtual and non-virtual, to have objects that we can refer to either boxed or unboxed, these choices make C++ complex. And this is why in Java we always have boxed objects with always virtual methods. So Java uses dynamic dispatch always. This is also called late binding. And what we're doing here is using the dynamic type of the object or the actual type of the object in order to determine which method to invoke. This is in contrast with the default behavior of C++, which uses static binding or static dispatch or early binding, and these use the static or declared type of the variable to determine which method to invoke. These two concepts are important. You can see they have lots of names, so anything with lots of names is typically important. And early here refers to the compilation process. Late refers to the runtime process. And of course, those are the same things we mean when we say dynamic, that's runtime, and static is typically compile time. So static is early, dynamic is late. As a second example, let's suppose I have a function interface and three realizations of that function. I can, of course, create an array of instances of these three function types and now iterate through the array, invoking the function repeatedly. And here I'm just going to print out the number and the particular function that I'm calling, and I'm going to apply that function to 20. And what I should get out is 21, 22, 23. We can also write this without using explicit classes. We could use an anonymous inner class because the functions are only differing here in terms of what they increment, not what they're doing. Just we can use a value for this. And so let's loop through the three elements that we want to put in. Of course, we need an effectively final field to put into the closure for each of these. So I'll use J here. And we can create the functions we want. We can invoke them. And here I'm using the inner class notation. And of course, in Java 8, we can use the lambda, which is a little bit lighter, but does the same thing. Class-based languages have two different methods for code reuse. One of them is common among all languages. Class-based languages, object-oriented languages, functional languages, every kind of language has the first mechanism, which is called delegation or composition in the object-oriented context. And this just means I have a variable that stores a reference or a pointer to another object or function, and I somehow use that object or function. This is super common. It just means I have a reference I can pass around and I can use or invoke that thing. You can think about a bird having, say, a wing, and the wing is strapped onto the bird via a reference or a pointer, and when the bird wants to fly, it causes its wing to flap. This is a very standard idea of constructing an object or a complex thing by components. Class-based languages also have a second mechanism which is unique to them called inheritance. And this is where you can describe the properties or the function of an object by layering its definition among multiple classes. A common property of all animals would be some sort of metabolic process. For example, let's suppose we have some basic way of processing food. When the bird was asked to eat, it might actually have some specific bird eating pattern. For example, finding bird seed or worms, whatever that bird likes, and then use the inherited metabolic process in order to process that food. Inheritance can be quite handy, but it's also a little bit tricky sometimes to code up because I'm using multiple views of the same object. So when I have this kind of inheritance, I'll have my bird class, but I also have the bird as an animal. And it can get complex because methods can be overridden or abstract or final in these different classes. And I'd like to just go through what all that means. So let's just start off with a simple animal class here. We'll have two methods, f and g. And f is going to be recursive. And what we're going to do here is print out f with its argument. And then if the argument is 0, we will call g. Otherwise, we'll call this recursively, reducing the argument by 1. And you can see g here just prints itself out. So if I create an object of this class and invoke f, I expect f2, f1, f0 to be printed, and then we'll just print g. We can actually type this into the J shell and see what it does. If you've never used J shell, it's a lot of fun. You've got an interactive version of Java. And when I actually hit the return key here, I get the output, and it's what I expected. So 2, 1, 0, and then g. You can see it's also printing the result, which is the result of this function. And the result here is 0. We're getting that from g. Note that we're just returning the result that we get from each of these calls. So what we have here is recursive calls calling each other, each of them just returning 0. So let's now extend the animal class here with a bird. And my bird here is going to override one of the two methods here. I'll override g on line 10, but I'm going to leave f alone So f is an inherited method for birds. On line 12, we'll create a bird and then store that in a variable of type animal, and then we'll invoke the function f. So what does this do? Well, it depends on what kind of dispatch we have. In Java, which I've written here, we do dynamic dispatch. And that means that the function we're going to invoke here depends on the dynamic type of the variable. Well, that's pretty obvious because there's only one definition of f, so it kind of doesn't matter for f. But what happens when I invoke this.g here? Well, when I invoke this.g, I could actually hit one of these two methods, either the g on line 6 or the g on line 10. Which one is it? And you can see that there will be a difference here because in class A, this, of course, has static type A. When we actually invoke the method, however, we'll be on an object of type B. And therefore, we have a different static type and dynamic type for this. Since Java is dynamically dispatched, we will prefer the dynamic type, and therefore, this is going to eventually print out BG. When you have a class like animal here that's intended to be subclassed, it's common to mark that class as abstract. You don't actually have to do anything else, but simply by marking this class as abstract, you change its meaning. In Java, an abstract class cannot be instantiated. So if you attempt to instantiate this class directly, you'll get a compiler error. In order to use an abstract class, we have to create a concrete subclass and instantiate that. Inside of an abstract class, I can also define some methods to be abstract. And the convention here is that abstract methods must be overridden in any concrete subclass. So if I attempt to define my bird class here that does not provide an implementation of the abstract method g, again, I'll get a compiler error. G is a method that must be overridden. We also have the capability to specify a method that may not be overridden. F here is a final method, and if we attempt to override it, we'll actually get a compiler error here as well. So the methods that we can override in Java have two different forms. They're either non-final concrete methods or abstract methods. We can refer to these non-final and abstract methods as hooks, which are places that subclasses can change the code or the behavior of the superclass. In this case, I've overridden both of these methods, f and g. And you can see that when I do this, and I invoke the method f on the bird, well, it's not going to use the method f in the abstract class A anymore. We're going to use the overridden method that we provided directly in the bird class. Note that this behavior doesn't change if the class A itself is concrete and actually provides its own implementation of G. It's common for subclasses to want to use some inherited behavior from a superclass in order to define their own new behavior. So you can imagine f is a feeding method, and in order for the bird to feed itself, it might use some inherited metabolic process of the animal class. And we can attempt to do something like that by trying to invoke the f method of the superclass. And if we do that using the this variable, well, what's going to happen here? Unfortunately, not what we want, because this in class B is both statically and dynamically going to be a B. And what that means is where I'm going to simply do a recursive call here, which is not exactly what I intended. We're going to end up with an infinite loop. So how can I actually invoke the method of the superclass? Every class-based language provides a mechanism for this. In Java, it's called super. When I execute this code, we're going to call f of class B, because B is the dynamic type of X. And we're then going to execute the code, printing out B of f. Then we're going to do a super call. Now note the super call is going to dispatch up here and invoke the f of the superclass, as you would expect. That's all well and good, but what happens when I do this recursive call to this.f? Right? Again, we're in this interesting situation. This is dynamically a bird, but statically an animal. Which method gets invoked? Well, Java does dynamic dispatch. It hasn't changed. So we're going to go back down to this f, and that f will execute, then go back up to the superclass. So the superclass f gets invoked. We'll print out a again, and now again invoke the subclass f. So this process of bouncing back and forth between sub and super as we do these recursive calls will eventually look like this. Note we're alternating B, A, B, A, B, A until we finally get to G. At that point, the recursion terminates, resulting in 0. This kind of tight interplay between sub and superclass is characteristic of inheritance, and it's actually pretty tricky to emulate using composition or delegation. Let's look at how one might try to do that in Java. To use delegation, I don't extend A, and I don't use super. Instead, I'm going to give my bird a private animal interior object and use that animal interior object to invoke f. And this should behave similarly to what I had before, but it's not exactly the same. And why not? It's because of what happens on this recursive call in A. Note that that is a separate object from B. I don't have a single object of class B that is also of class A. No, now I have two objects, one of class B and one of class A. So when f is invoked here on line 4, it's invoked on an object that is both statically and dynamically of class A. And therefore, the recursive call here will simply recur on A of f directly. And you can see that in the output. When we start with b.f, we'll invoke the method and then call the method on the inner A object. That will then just recur on itself until it terminates, at which point we're done. You'll also note that the call to this.g is different. Oops, because here, this again is both dynamically and statically of type A. So I'm not actually getting the call to b.g like I had before. How would you do this in a delegation-based approach? Well, it's actually fiddly because I need A to know about its subclass B. And doing this in Java is maybe more trouble than it's worth. I've done this by creating an interface so that A doesn't need to know about the specific subclass B. It just needs to know about something that has an F and a G. When I have an interface, I have to denote things as public, so that's rather annoying. But I also need to record the back pointer. So what's going to happen here is A needs to know how to get back to whoever is invoking it. And so there's different ways to do this kind of plumbing, but what I want to do essentially here is call back.g and back.f rather than calling this.g and this.f. And I'll initialize back initially to this, but I'll update back when necessary. So here I'm going to update back to point to the B object after I create that A object. So this is just something we're not going to do. If you want to actually have this behavior, this is the use case for inheritance in a class-based language. It's not something we really want to do using delegation. There's just too much plumbing here. So you may wonder about poor JavaScript. It doesn't have primitive classes, so what is it going to do in this case? Well, delegation-based languages make this kind of thing easy using the prototype chain. So in JavaScript, there is a super keyword, but it's based on the prototype chain rather than this static class hierarchy. So we can achieve this in JavaScript without any real pain. This is one way to cut it up. There's other ways. In 1995, when Java was released, there's also a significant book released in software engineering literature called Design Patterns. It's affectionately known as the Gang of Four book because it has 4 authors. And that book advocates the use of object composition over class inheritance. And what they really mean by composition is delegation, the way we've just been talking about it. And one of the main reasons for this is that there's more dynamism possible. Older class libraries are written with inheritance in mind. It's still useful in some cases where we have very closely interacting behaviors, but delegation is a more general pattern. And many modern libraries do prefer composition or delegation over inheritance. You'll still find class inheritance, though, used in a lot of software. It's used in a lot of the older Java APIs in particular because this trend really started after the Java libraries had been initially finalized. One example is how input works in Java. You have an input stream class, and the input stream represents a stream of bytes. The method read is abstract here, and therefore the class is abstract. And the read method is supposed to give us 1 byte. We've got methods that use that method read. This one will read a sequence of bytes of a certain length. Skip will skip along and throw out bytes of a certain length from the stream. And the documentation tells you more or less what these do. So applications that need to define a subclass of input stream must always provide a method that returns the next byte of input. The read method that accepts the length argument in class input stream simply calls the method read repeatedly. Likewise, skip. Subclasses are encouraged to provide more efficient implementations of these methods. So here you can see an abstract method that's a mandatory hook. You must override this method. And you also have these other non-final methods, which are given as options to the programmer, the extender of this class. You may want to override these. In an example, I don't have to override that method. Here I've written just the read method, and I'm going to use in my client class the read method, which takes a length. So here I'm just overriding the basic read method. What I'm going to do is just give you an infinite sequence of characters. These are ASCII characters, the printable ones. Here I'm going to create a buffer of size 50 and then read in 50 characters at a time. And so if I read this in 3 times, I'll just end up invoking that read method, 150 times. So it's actually just continuously invoking that. And this is using the relationship between the sub and the superclass.